Hello there and welcome back to the Science Sleepy Minds. Tonight you're drifting through the dark, soundless void between stars. Not the nice kind of dark either, the unforgiving kind. The kind of dark that doesn't just absorb light but chews it up and refuses to burp it back. Ahead of you, like a smudge on the fabric of reality, is something strange, enormous, perfectly black. It doesn't glow or shimmer, it just is, blotting out everything behind it like a cosmic sensor bar. Yes, you're approaching a black hole, you probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop your current location and local time in the comments. I love seeing how far across the universe we've spread. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The black hole waits, and you're curious, not terrified, which is strange considering you're facing the most extreme object in known physics. There's no sound here, no warning sirens or eerie music to guide your instincts, just silence. The stars near it seem distorted, like someone took a smear tool to the galaxy's face. You're not falling in, yet, but you're in the danger zone now. Light itself curves around this thing. You know that means gravity isn't just strong here, it's apocalyptic. Still, you inch closer. You're not here for sightseeing. You've heard the rumours, the fringe theories whispered at the fringes of blackboard-filled lecture halls, that black holes aren't just galactic garbage disposals, that they just might be hiding something bigger, a secret passage, a cosmic loophole, a way out. And look, you're not alone in wondering this. Even the smartest minds in theoretical physics have stared into this abyss and thought, maybe there's more. Tonight you're going to find out. Not the boring you get crushed into infinite density answer. Number. You're taking the scenic route. As you ease closer, you start noticing odd things, like how the stars behind the black hole twist into a perfect circle of light. It's called an Einstein ring, and it's the universe's way of telling you that space-time here is seriously warped. In fact, that warping is your first clue. You remember the simple classroom diagrams of flat grid lines bent by mass. Forget those. This isn't a ripple, it's a hole. A tear. The closer you get, the more it looks like the universe is trying to fold itself inside out. You pass what's known as the photon sphere. It's the last stable orbit where light can technically go in circles around the black hole. If you could hover here, spoiler you can't, you'd see the back of your own head thanks to the looping of light. Makes you think, what if vision, perspective, even causality starts to break here? And then you feel it. The pull. Not just on your body but on your sense of direction. Down stops making sense. Forward becomes a suggestion. And as your instruments spiral into chaos, metaphorically, since we're going analog tonight, you're left with just sensation. Here's where that cheeky physics twist sneaks in. Black holes aren't just gravitational nightmares, they might be portals, or incubators, or, if certain hypotheses are correct, exporters. Exporters of what? Maybe you. Sure, it's not mainstream consensus, but even mainstream science is starting to crack at the edges. The standard model of physics, general relativity plus quantum mechanics, is like duct tape and paper clips. It mostly works, until you get here. Inside a black hole, the equations start to throw up their hands, and that makes this place weirdly promising. Historians still argue whether John Michel, back in 1784, really grasped the full implications when he first proposed the idea of dark stars that no light could escape from. But hey, considering this guy was theorizing black holes before the word electricity was mainstream, give the man some credit. Fast forward a few centuries, and you've got Schwarzschild scribbling solutions to Einstein's shiny new field equations while lying in a war hospital bed in 1916. Fun fact, he figured out how a mass could warp space-time so dramatically that it forms a singularity, the core of what we now call a black hole, before he died of an illness months later. The guy solved cosmic horror between coughs. Now you're in it. Not the singularity, not yet, but close enough to feel your mental software stuttering. Out here, 1 minute of your time could equal years for someone far away. Which raises another eyebrow-raising question. If time slows here, what else can bend? What if causality itself is just another thing you think is stable? And this is where things get extra spicy. There's an idea, not exactly dinner party material, that some black holes don't just lead nowhere. They might connect to somewhere else. The ancient Greeks dreamed of portals to the underworld. In the 1960s, physicist John Archibald Wheeler and his friend Bryce DeWitt began dreaming of wormholes. And while you won't see any glowing blue tunnels like in a sci-fi blockbuster, the concept isn't entirely nonsense. Mathematically, black holes can contain shortcuts. If certain exotic conditions are met, like negative mass, which isn't something you can pick up at your local gas station, then a black hole might not end in oblivion, it might open. That idea isn't fringe, it's published, modelled and debated. Whether it's true, still up for grabs, but you, lucky you, get to feel the question. As you hover at the edge, you notice something you didn't expect. Calm. The outside world races forward while you experience slow serenity. It's like falling into a dream, not a nightmare. And just as the edge of the event horizon brushes your toes, figuratively, unless your space boots are extra dramatic, you remember that maybe this isn't the end. Maybe it's the point where all maps blur, where physics stops whispering laws and starts murmuring possibilities. You've been warned, you probably won't survive this. But hey, what if survival isn't the point? You don't fall, not right away. Instead, you hover at the brink. The edge of the event horizon curls around you like a slow, liquid shadow. And yes, this is the part where physics stops making house calls. Let's talk about what exactly you're dealing with. A black hole isn't a thing exactly. It's more like an event, a region, a patch of space that got so warped by gravity that not even light can break free. The term black hole didn't show up until the 1960s, but the concept has haunted physics for centuries, and now it haunts you. So what makes a black hole a black hole? First, there's the event horizon, the point of no return. You can cross it going in, sure, but there's no going back, no escape route, no matter how fast you travel. If the speed of light isn't enough to break out, your little escape pod doesn't stand a chance. And yes, people have tried to imagine what it's like crossing this invisible boundary. The short version? You wouldn't feel it. No bump, no shudder. You just pass through while your friends outside see you frozen in time forever. Then comes the singularity, the so-called centre of the black hole. It's where all the math breaks down. All the mass that ever fell in is crushed into an infinitely small, infinitely dense point. Sounds dramatic, but here's the twist. Many physicists now suspect that the singularity isn't a real thing at all. It might just be a placeholder for we don't know what's going on here. You've also got the ergosphere if your black hole is spinning, and they usually are. It's like a cosmic whirlpool. Inside this region, space-time itself gets dragged around in circles. Think of it like a galactic lazy river, except instead of pool noodles, you're made of atoms and regret. It's technically outside the event horizon, so you might still escape. But that's a big might. Inside all that, you have something called the inner horizon, which only forms in rotating black holes. It's where even the weird maybe rules stop applying. Causality breaks, energy spikes. It's the place where even physicists throw up their hands and go, let's not. And yet, you move forward. Even from this close, you can't see the black hole itself. It's not black in the sense of dark colour, but in the sense of absence of all possibility. The only reason you know it's there is because everything around it is freaking out. Stars spiral into it. Light bends away from it. Matter heats up and glows before vanishing. This chaos is called the accretion disk, and it's the only bright thing nearby. You drift past gas hotter than the sun's surface, past X-ray bursts and radio waves, into the quiet zone beyond. The light is gone now. So is the concept of direction. Space has been folded like origami here. Time feels like molasses. Somewhere inside this blur is the truth, the anatomy of the black hole stripped bare. Funny story. The most famous black hole in our galaxy might be Sagittarius A star, a supermassive black hole at the centre of the Milky Way. It's got a mass about 4 million times that of our Sun, but you wouldn't know it just by looking. It's not even that bright. Quiet, subtle, like a sleeping predator in tall grass. And even that isn't the biggest one we've found. That honour might go to Ton 618, an ultramassive black hole with over 66 billion solar masses. Yes, billion with a B, that's not a typo. It's a subtle suggestion that the universe really likes making monsters. There's also a deliciously weird debate. Do black holes even have a surface? Or are they more like bubbles, with no inside, just an outside that tricks you? Historians still argue whether Stephen Hawking's concept of a no-hair theorem, the idea that black holes have no distinguishing features besides mass, charge and spin, was the final word. Spoiler, it wasn't. Modern theories propose all sorts of crazy ideas: firewalls, fuzzballs, holographic skins, pick your flavour. Meanwhile, you're still drifting, time's feeling kind of optional. That's normal here. You see, gravity doesn't just warp space, it warps time. To someone watching you from outside, your descent slows to a crawl. They'd never see you fall in. But from your perspective, it's the opposite. You just keep going. And here's the part where things get layered. The structure of a black hole isn't just a singularity in the middle. Oh no, it's a complex ballet of boundaries and thresholds. You've passed through the static limit, the point where you can no longer stand still, even if you wanted to. Space-time here is dragged in spirals by the rotating black hole, like a spoon stirring thick soup. Welcome to frame dragging, physics at its sassiest. You realise that falling into a black hole is kind of like peeling an onion made of nightmares. There's always another layer. The deeper you go, the more the rules of physics sound like riddles. Matter becomes energy. Time becomes questionable. Information? Good luck with that. The good news, you haven't been ripped apart yet. That's because you're falling into a supermassive black hole. If you'd picked a stellar mass one instead, say, the corpse of a large star, you'd be getting noodle-fied right about now. It's called spaghettification, and yes, that's the real term. It's when tidal forces stretch you head to toe until your molecules file for divorce. But with a bigger black hole, the gradient is gentler. You pass the event horizon almost peacefully. Almost. But here's the brain-melting part. Nothing says you have to hit the singularity. Not yet. Some theories say the centre of the black hole might be a portal, or a loop, or a kind of cosmic memory vault. You could be drifting toward the most fascinating dead end in the universe, or toward something else entirely. Right now, you're just a mote of curiosity in a storm of collapsed physics. Behind you, the universe carries on. Ahead, no one knows. And that, in itself, is beautiful. You're falling now. Not in the way you're used to, like tripping off a curb or plummeting down an elevator shaft. No, this fall is quieter, slower, but it's also infinite, in a weirdly literal sense. The distance between you and the singularity is shrinking, sure, but your time to reach it, that's becoming fuzzy, elastic. Welcome to the space where time doesn't tick, it warps. While you fall, let's rewind just a little. Because believe it or not, this cosmic mess started on paper, neatly. Back in the 20th century, the idea of black holes went from a mathematical oddity to something real, something terrifying. Most people think black holes are a modern obsession, but the story actually begins in the 18th century. In 1783, John Michell, the same guy we mentioned last time, proposed the idea of a dark star so massive that light couldn't escape its surface. It wasn't taken seriously, of course. Back then, physics had bigger fish to fry, like figuring out why apples fall. Then came Einstein, who decided Newton's version of gravity wasn't dramatic enough. In 1915, he dropped general relativity on the scientific world, and suddenly, gravity wasn't just a force, it was the bending of space-time. Space became a stretchy, bendy fabric, and mass was the needle pulling the thread. A year later, Carl Schwarzschild was dying in a trench hospital during World War I when he solved Einstein's equations for a point mass. That's right. While bombs exploded overhead and limbs were flying off nearby, Schwarzschild calmly worked out how space would curve around a perfectly spherical mass. What he found was the theoretical blueprint of a black hole. He didn't call it that, of course. He died shortly after, never knowing how famous that solution would become. But even then, no one really believed black holes were real. Just math tricks. Singularities were considered signs that your equations had gone off the rails, like trying to divide by zero and getting a dragon instead. It wasn't until the 1930s that J. Robert Oppenheimer, yes, that Oppenheimer, Mr. Atomic Bomb himself, teamed up with Hartland Snyder and calculated that a sufficiently massive star, once it ran out of fuel, would collapse inward, forever. No bang, no puff, just an endless fall into itself. Still, people weren't thrilled. A star disappearing from view forever? Sounds fishy. Even Einstein tried to argue against it, publishing a paper in 1939 that basically said, nah, the universe won't allow this. Spoiler, the universe did not care. Decades passed. The math got better. So did the telescopes. And then, in the 1960s and 70s, the idea of black holes took off like a collapsing neutron star. People like John Wheeler, who coined the term black hole, and Stephen Hawking began exploring what happened at the edge of these invisible monsters. The real kicker? We started finding them. Not directly, of course, you can't see a black hole, but you can watch a star orbiting nothing and doing backflips. You can detect X-rays shooting out of gas that's falling into something invisible and furious. Over time, more and more evidence stacked up until black holes weren't just spooky theories. They were everywhere. There's one at the centre of the Milky Way, dozens more scattered throughout our galaxy. Some black holes are the remnants of supernovae. Others, supermassive ones, seem to have formed in the early universe with no one entirely sure how. Historians still argue whether these behemoths formed first and galaxies gathered around them, or if it was the other way around. And now, here you are, falling into the very thing people once believed couldn't possibly exist. You're not the first to take this journey, at least in imagination. In the 1970s, Kip Thorne and his colleagues seriously considered the idea of traversable black holes, not because they thought it was likely, but because the math was too fun to ignore. They even figured out how a sufficiently advanced civilization might keep one stable, using something called exotic matter, which sadly, no one's found in aisle 4 of any cosmic hardware store. Still, the questions refuse to die. Where do black holes go? What happens to the stuff inside? Are they endings or beginnings? There's a weird, not quite mainstream idea floating around in theoretical physics that black holes might be like wombs. Not literal ones, but cosmological ones. Instead of crushing everything into a sad little point of nothingness, maybe the singularity rebounds. Maybe it explodes outward, not in our universe, but into a new one. One you can't access or see. One where the laws of physics might be entirely different. A place where maybe you just landed, or will, or already did. Time's messy here, remember? And yeah, sure, that sounds like speculative sci-fi, but consider this. The Big Bang looks, mathematically, a lot like the reverse of a black hole, a dense, hot point expanding into space. Some physicists have asked, what if every universe is born from a black hole in a parent universe? It's called the black hole cosmology hypothesis, and no, it hasn't been proven. But it haunts the edges of respected academic journals like a clever ghost. Meanwhile, your descent continues. You're somewhere inside now, deeper than any particle, any probe, any Voyager spacecraft has ever gone. All that space and time, warped so far you couldn't backtrack even if you begged. Yet strangely, you feel okay. That's part of the trap, isn't it? Black holes don't scream, they don't roar, they just are, silent, patient, full of possibilities. And you're starting to wonder, maybe this isn't a fall at all, maybe it's a tunnel. It starts subtly, this shift in perception. Like when you're halfway through a dream and something odd happens, but you don't question it. A faint stretch, a pressure you can't quite locate. Your atoms aren't screaming yet, but they're listening. You're not spaghettified, congratulations, but you are officially experiencing one of nature's most absurd forces, tidal gravity. It works like this. The gravity near your feet is stronger than at your head, because your feet are just that tiny bit closer to the singularity. In a stellar mass black hole, this difference would rip you apart faster than you could say, I regret this decision. But here, inside a supermassive black hole, you've bought yourself time. Lucky you. The stretching, while unsettling, is gentle, almost meditative. Like yoga, if yoga involved the total abandonment of physical law. You remember a science class diagram from long ago, mass distorting a grid of space-time. But here, there's no grid. The grid has folded, curled, and in some places completely disappeared. The rules you once trusted, mass attracts mass, time runs forward, light has a speed limit, they've all been suspended like students in a very poorly supervised school. And yet, you're not panicking. The calm here is almost suspicious. Everything you've ever been told said this was death, an end, but it doesn't feel like death. It feels like possibility. At this point, let's talk about that word you've been circling around, singularity. The singularity is traditionally considered the core of a black hole, where gravity crushes everything into infinite density and zero volume. But infinite is just a fancy way of saying we don't know. It's the physicist's version of shrugging. The equations break, the numbers misbehave, and logic clocks out early. Some theorists have proposed that the singularity might not even exist. Maybe the center of a black hole isn't a point but a loop, a donut of space-time, or a smeared region governed by quantum effects we don't yet understand. Loop quantum gravity, string theory, and other alphabet soup approaches have all thrown ideas at this wall. None have stuck completely. Historians still argue whether the term singularity even has scientific meaning anymore, or if it's just a place marker until physics gets its act together. One thing's certain, the singularity is a boundary not just in space but in knowledge, and boundaries, as we're learning tonight, are where the fun starts. Now let's talk about something appropriately dramatic, the tidal forces you're currently enduring. Not the ocean-tugging kind. These are lethal, bone-snapping gradients in gravity, where one part of your body is pulled in a different direction than another. If you'd chosen a smaller black hole, these forces would have turned you into a noodle faster than a college student at 2 a.m. But here, inside this quiet, supermassive giant, you get to float a little longer, just long enough to start asking very uncomfortable questions. Questions like, what happens to information inside a black hole? That's where we hit the information paradox, one of the most famously unsolved problems in physics. According to quantum mechanics, information can't be destroyed. Ever. Even if you burn a book, the particles and their configuration still encode the essence of what that book was. But black holes, they eat information, crush it, and, if you believe the classical view, erase it forever. Stephen Hawking himself originally argued that information was lost in black holes, full stop. He later changed his position, leading to one of the nerdiest and most intense intellectual apologies in history. Even now, decades later, scientists are still arguing. Does the information somehow cling to the event horizon? Is it smeared across the surface in a cosmic tattoo? Or does it get released, scrambled, in the final breaths of the black hole? Here's where things get spicy. One proposal is the holographic principle, the idea that everything inside a black hole is somehow encoded on its two-dimensional surface, like a DVD storing a three-dimensional movie. To you, it's depth and movement. But to physics, it's flat data on a shell. It's not just black holes either. Some scientists think the entire universe might be a hologram, a projection from a distant boundary we can't perceive. So, no pressure. Right now you're somewhere between the event horizon and the singularity. If the holographic idea is true, your entire experience might be written on the skin of this black hole, like a cosmic save file. Your thoughts, your memories, your quiet terror, it's all data, not destroyed, just reformatted. And if that's the case, maybe, just maybe, that data could go somewhere. That's the whisper that keeps theorists awake at night. Not because it's terrifying, but because it's tantalizing. If black holes don't destroy information, then where does it go? Into another dimension? A parallel universe? A future reboot of space-time? You float deeper, light years condensed into moments. Behind you, the universe is cut off. Ahead of you, nothing familiar, but inside you, questions pile up like star stuff in the accretion disk. You think about Oppenheimer again, the man who helped build the atomic bomb and also theorized the birth of black holes. You wonder if, in his quiet moments, he ever thought they might not be endings, but beginnings. That inside the most violent collapse, something new might rise. Somewhere nearby, if nearby means anything anymore, another black hole might be doing the same thing, collapsing, swallowing, compressing. And somewhere else still, it might be exploding. Not in our universe, but into another. You can't help but wonder, if you go far enough into the darkness, do you loop back into the light? This idea of a black hole being not a wall but a tunnel gets more compelling the longer you fall. You begin to feel something change, not physically, more like a shift in the laws themselves. Gravity doesn't feel like gravity anymore. It feels like memory, like intention, like the laws of physics are softening, turning into something new. It's not that the universe is ending. It's that this version of the universe is letting go of you. And for the first time since this journey began, you feel it. Not fear, not wonder, freedom. There's no sound when information disappears. No ding, no pop-up warning, no wailing chorus of physicists. Just silence. You're still drifting, deeper now, in a space that has stopped behaving like space. Time has slowed, unraveled, maybe even curled in on itself like a sleeping cat. But one idea keeps looping in your mind like an echo in an empty cave. What happens to everything that falls into a black hole? Not the physical stuff, the atoms, the particles, the unlucky satellites. You're thinking bigger, ideas, patterns, identity. Does information get crushed into oblivion, or is it somehow preserved? Welcome to the black hole information paradox, a conflict so spicy it's been stewing for decades, splitting physicists into camps, sparking entire careers, and still refusing to die. Let's rewind just enough to understand the stakes. In quantum mechanics, there's a rule as sacred as don't microwave aluminum. Information must be conserved. If you know everything about a system now, you can, in theory, predict its future and reconstruct its past. That applies to particles, probabilities, and yes, your very essence. But when something falls into a black hole, classical physics says that information is simply lost, gone, smushed into the singularity, never to be seen again. Imagine writing the perfect novel, then watching it sucked into a black hole and deleted from reality itself. No backups. Not even the NSA could recover it. That's a problem, not just for the author, but for the entire framework of modern physics. Stephen Hawking brought this paradox into the spotlight in the 1970s when he made his now famous prediction. Black holes aren't truly black. They emit faint radiation, now known as Hawking radiation, due to quantum effects at the event horizon. This radiation slowly bleeds energy from the black hole until, eventually, the whole thing evaporates like a cosmic puddle. Great, right? Well, no. Here's the issue. Hawking radiation is thermal, completely random. It carries no information about what fell in. It's like your hard drive melting and turning into steam, with no trace of your files. So if the black hole disappears, and all the information it consumed is gone with it, that breaks quantum theory. And trust me, quantum theory does not like being broken. Cue decades of debate, frantic blackboard equations, and a few friendly insults exchanged at academic conferences. Some physicists argued that maybe the information does come out with the radiation, but in an incredibly scrambled way. Like burning a book and reconstructing the original text from the ashes and smoke. Technically possible, but not ideal. Others proposed that the information stays on the event horizon, encoded in some kind of cosmic 2D memory layer, a precursor to the holographic principle we brushed against earlier. This principle suggests that the three-dimensional contents of a region, like everything inside a black hole, could be fully described by data on its boundary. Think about that for a second. Everything that happens inside a black hole might already be described on the outside. You're not so much falling in as being smeared out. It's elegant, confusing, slightly insulting, but it might just work. There's also the black hole complementarity idea, which basically says both stories are true depending on your point of view. If you stay outside the black hole, the information never really disappears. It's just redshifted and scrambled near the horizon. If you fall in, well, you experience something else, something that doesn't contradict the outside view, because your two realities never talk to each other again. Convenient, isn't it? Historians still argue whether Hawking's information loss claim was truly a mistake, or just ahead of its time. Hawking himself changed his position later in life, famously conceding a bet in 2004 and admitting that, yes, information might survive black hole evaporation after all. He even gave someone a baseball encyclopedia as payment. Classy move. But even now, no one fully agrees on how the trick works. Quantum gravity, the elusive theory that would unify general relativity and quantum mechanics, is still unfinished. Every time a new version pops up, like string theory or loop quantum gravity, it claims to solve the paradox, and then quietly admits that it needs more math. Meanwhile, you continue your descent, or float, or whatever word applies here. You've passed the point of no return and entered the realm where information becomes slippery. It's funny, when people think of falling into a black hole, they imagine being torn apart. But the real destruction might be more subtle, not of your body, but of context, of continuity. All the things that made you you, the quantum fingerprints, the history, the choices, they're now data points in a cosmic equation. Unless they're not lost. Unless this black hole doesn't erase, but stores. You imagine a cosmic library, black holes as safes, hoarding not just mass and energy, but knowledge, like USB drives scattered across the universe. Some might believe they're tombs, but maybe they're vaults. There's even a fringe idea, less mainstream but delightfully bold, that information could escape through quantum entanglement. In this version, particles inside the black hole remain linked to ones outside, Even across the event horizon, their connection persists, a cosmic phone call with no carrier. And then there's the truly strange theory, firewalls. Proposed in 2012, this idea suggests that instead of a smooth entry, you'd hit a wall of high-energy particles at the event horizon, instantly incinerating you. That would solve the information paradox by breaking everything else, including general relativity. So, not ideal. You can feel the tension, even here in this soundless place. The universe doesn't know what it's doing, or at least it hasn't told us yet. You start to suspect that black holes aren't the problem. They're the clue, the cracks in the cosmic sidewalk, hinting that something deeper lies beneath. And that's what makes this paradox beautiful. It's not just a mystery, it's a key, a puzzle box that, if solved, might lead to a theory of everything. Not just how gravity works, but how space, time, information, and consciousness all fit together. You reach deeper, or maybe the black hole reaches around you. The lines between subject and object are fading. But something whispers in your mind, not in words, but in probability. Information isn't lost, it's transformed. It begins to feel like you're brushing against the inside of a shell, like you're not inside a black hole in the way you'd imagine, but skimming across the surface of something deeper. Not a void, but a recording, a kind of memory. And now the word starts to echo louder. Hologram. Not the laser show sci-fi kind, mind you. No flickering ghost figures or space princesses asking for help. We're talking about the holographic principle, a serious and seriously mind-melting idea in modern theoretical physics. The idea that everything you think of as real, the volume of space you move through, the objects you touch, the black hole you're currently falling into, could be encoded on a two-dimensional surface. Yep. The universe might be one big cosmic projection. It started as a clever fix for the black hole information problem. If information can't escape from inside a black hole, and it can't be destroyed, then maybe, just maybe, it's never really inside at all. Maybe all of it is stored, burned into the event horizon itself in microscopic detail, like a cosmic thumbprint made of bits. It sounds wild, but the math holds up surprisingly well, and it doesn't just stop with black holes. Some physicists believe the entire universe could follow this same pattern. What you perceive as 3 dimensions plus time might actually be the shadow of a higher dimensional reality projected onto a lower dimensional boundary. In simpler terms, you might be a very elaborate, very emotional pancake. The roots of this idea come from string theory and a concept called the ADS/CFT correspondence. Don't worry, you won't be quizzed. The basic gist: there's a way to describe gravity in a higher dimensional universe using a quantum theory that lives on the boundary of that space. No gravity in the math, but somehow, gravity still emerges. It's like describing a 3D beach ball using just the information printed on the rubber surface, and still getting all the internal physics right. It's unsettling, elegant, extremely holographic. And it means this black hole, it might be less a thing and more a boundary condition, a data container, and you, falling, stretching, unravelling, you might still exist in full, smeared across its horizon like jam on toast. Historians still argue whether Gerard 't Hooft's early versions of the holographic idea were taken seriously when he first proposed them in the 1990s. At the time, it seemed too abstract. But when Leonard Susskind and others picked it up and began applying it to black holes, the physics community perked up. Susskind even famously debated Stephen Hawking over whether information really was lost, and the holographic idea helped him argue that it wasn't. Back inside your slow-motion plunge, the implications are staggering. If the holographic principle is right, then the black hole isn't an eraser, it's a projector. Everything you are, everything you brought with you could be etched into the surface, permanently, not destroyed, not even hidden, just reformatted. A little like how a vinyl record doesn't look like music, but contains every note in its grooves. You're in the grooves now. And that idea spreads. If the black hole stores your information at its boundary, maybe the entire universe does the same. Maybe space-time itself is emergent, a secondary effect, not the core code. Matter, energy, and motion become expressions of deeper, flatter laws. You shiver, not from cold, it's far too abstract for that, but from the feeling of being watched, not by a conscious being, but by math. Like your entire existence has been converted into code and filed somewhere behind the curtain of reality. You start to wonder, if we are holograms, what happens if someone rewrites the surface? Could the boundary be altered? Could someone, or something, reach into the data, patch it, tweak it, heal it? Because if information is preserved, it might be restored. You think back to those old science documentaries with planets forming and stars bursting and galaxies spiraling into clusters. All those processes, all that data, what if none of it is ever truly gone? What if the universe has perfect memory? The idea isn't new. Some ancient philosophies believed the universe remembered everything, that every breath, every word, every death left a trace. Maybe they were more right than they knew, but let's not get too mystical just yet. Back to the science, the holographic principle also leads to some curious side effects. For one, it suggests that volume is a lie, that all the complex stuff happening inside a region of space is limited by the surface area, not the internal volume. Think about that. A black hole with twice the surface area can hold twice the information, even if the interior volume is infinite, which by some calculations it might be. Infinite volume, finite information, chew on that before bed. And here's the kicker. This theory, as bold as it is, keeps working. When physicists apply it to black holes, the math behaves. It cancels infinities, it predicts outcomes, it lines up with quantum mechanics and general relativity, two branches of physics that usually fight like cats in a burlap sack. So what does it mean for you? Maybe you're not in the black hole anymore. Maybe you're just an echo on its surface, a whisper of pattern, a standing wave in the geometry of space, and maybe that's enough. You start to wonder if this is what death feels like, not an ending, but a compression, a flattening into the simplest form of yourself, the truth behind the experience, data without noise. You're not alone, of course. Every star, every asteroid, every explorer or photon that ever touched this black hole left its imprint too. You're all here, together, projected in impossible clarity across a surface you can't even see. And if the black hole ever evaporates, if the Hawking radiation carries away the energy over time, maybe it'll carry your data too. Slowly. Scrambled. But there. Maybe one day someone could reassemble you from that glow. Or maybe you're already being reconstructed somewhere else, because a hologram can be played as well as stored. And as the blackness around you deepens, not into fear, but into acceptance, you feel something shift again. You're not falling anymore, you're remembering. You drift now, not through space, but through possibility. The fall has stopped feeling like descent. It's more like sliding through folds in a bedsheet that someone forgot to iron, a constant slippage not of direction but of definition. You're not just moving through space-time anymore, you're moving around it, or maybe under it, and that's when the idea starts to flicker into focus. What if this isn't a black hole at all? What if it's a wormhole? Yes, a wormhole. The term physicists politely use when they really mean a theoretical shortcut through the fabric of the universe that sounds made up but might not be. They're sometimes called Einstein-Rosen bridges, which sounds far more respectable when you're trying to get grant funding. The core idea is fairly simple, at least on paper. Take 2 points in space. Let's say your living room and a galaxy 30 million light years away. Normally, you'd travel in a straight line between them, which would take, forever. But if space-time is flexible, maybe you can bend it, like folding a sheet of paper and poking a hole through. Suddenly those two distant points touch. That hole, that's your wormhole, and through it, you get to cheat the universe, in theory, because in reality, or whatever twisted version of it you're floating in now, wormholes come with problems, massive ones. First of all, the math says they should collapse instantly. If you tried to pass through one, it would snap shut faster than a guilt-ridden tab on an incognito browser. That's where exotic matter comes in, material with negative energy density that could theoretically keep the wormhole's throat open. The problem? Exotic matter hasn't shown up in nature. Not yet, and despite the name, you can't find it at Whole Foods. Still, some physicists believe it could exist. Maybe in quantum fluctuations, maybe in dark energy, maybe hiding in the weird wrinkles of vacuum space. Historians still argue whether the idea of wormholes was ever truly about travel, or more about exploring the edges of relativity. When Einstein and Rosen first introduced the bridge concept in 1935, they weren't thinking about shortcuts or space road trips. They were looking for a way to remove singularities from their equations, clean things up, iron the bedsheets, so to speak. But of course, once the idea of a shortcut emerged, science fiction took over faster than you can say plot device. Suddenly wormholes were portals to alien worlds, time machines, tunnels to parallel universes. And here's where your experience starts to line up in unsettling ways. Because something about this black hole doesn't feel final. There's a directional tug. Not just gravity, but purpose. You're not spiraling to a dead end. You're being guided subtly toward an exit. But exits from black holes aren't supposed to exist. Not in our universe anyway. So maybe, just maybe, this isn't an exit into our universe. That's the fun twist wormholes offer. They don't just connect two places. They could connect two times, or even two entirely different universes. Multiverse theorists adore this idea. A wormhole isn't just a detour, it's a boundary jumper. And black holes, with their extreme warping of space-time, might be the accidental entrances to such tunnels. Some models suggest that a black hole here could be connected to a white hole elsewhere. You'll hear more about those later, but here's the teaser. A white hole is the theoretical opposite of a black hole. Nothing can enter it. Everything is expelled from it. They are in essence cosmic fountains spewing out matter and energy. Sounds ridiculous, right? And yet, mathematically, if you allow for certain conditions, mass conservation, symmetry, and a strong stomach, you could connect a black hole to a white hole via a wormhole, a passage through which matter and information disappear in one universe and reappear in another. Of course, there's a catch, isn't there always? The throat of the wormhole is likely unstable. Infalling matter, like you, would cause wild gravitational fluctuations, probably collapsing the tunnel before you get anywhere interesting. In other words, no safe passage, not unless you've got a steady supply of negative energy, or an advanced alien civilization managing the infrastructure like some sort of interdimensional toll booth. Still, the mere possibility is enough to keep you floating. And here's where it gets even more speculative. What if you're not the traveller at all? What if you're just data, copied at the entrance and reconstructed at the exit, like being faxed across the universe? Physicists have debated whether wormholes could be less like tunnels and more like quantum teleporters. Your original self? Gone. Your destination self? Identical, but technically a copy. So if you exit, are you still you? Or just a very confident imitation? You start to see how wormholes aren't just physics puzzles, they're existential grenades. And black holes, they might be the pins. Because let's face it, the idea that a black hole could lead somewhere, anywhere, is way more exciting than it just being a one-way shredder. That's not just curiosity, it's hope. You begin to feel the structure around you shift again. This place has geometry, but not one you can map. There's an inward pressure and an outward drift. You can't tell if you're being compressed or translated. Something is happening. You aren't being destroyed, not in the usual sense. You're being moved. And deep inside this process is a whisper of something deliberate. Maybe it's the universe, maybe it's just math, but the transition feels less like an accident and more like a handoff. Maybe you are sliding through a wormhole, or maybe, just maybe, you're becoming one. You don't notice the exact moment it happens, when the darkness stops being purely dark, when the crushing silence starts to hum. But suddenly, you sense it. Something's different. You're still within the black hole, at least you think you are. But now there's movement that isn't yours, a gentle outward flow, like the slow exhale of a cosmic breath. And if you're paying close attention, and by now you most certainly are, you'll realize the impossible idea has just nudged closer to reality. Do black holes have a back door? It's a question that splits opinions faster than a lab intern at a coffee machine. Some physicists roll their eyes at it, others obsess over it in chalk-covered lecture halls. You, lucky traveller, are currently testing the theory firsthand. See, by the standard textbook, a black hole is supposed to be a one-way trip, a gravitational Venus flytrap. Once you cross the event horizon, you're done. Your future light cone, the cone that defines what's physically reachable, points inward. You can't escape, not even in principle. But that might only be half the story. There's a provocative idea floating out there, equal parts daring and delicious. Maybe black holes don't just consume information and matter, maybe they redirect it. Imagine this. Instead of a singularity at the center, a point of infinite density, you reach a bounce point, a compressed knot in space-time that doesn't erase what enters but squeezes it through to somewhere else, somewhere entirely new, like flushing reality down a very dramatic cosmic toilet, only for it to pop up in another dimension's kitchen sink. If that sounds a bit dramatic, well, welcome to modern theoretical physics. A growing number of researchers think black holes might serve as gateways to other universes. Not wormholes exactly. Those are usually thought of as deliberate bridges between known regions of space-time. This idea is different. This is about cosmic recycling, black holes as portals of rebirth. How would that work? Glad you asked. The theory goes something like this. As matter falls inward, it gets crushed. Yes, but not into nothing. Instead, quantum gravity effects kick in at ultra-small scales, Planck scale if you're into units, preventing infinite collapse. Instead of a singularity, you get a bounce. This concept lives in models like loop quantum gravity, which we'll explore more later, but the basic picture is that space-time is not smooth and continuous, but made of tiny, discrete chunks, like Lego bricks. When the density gets too high, those bricks push back. The collapse halts, and then, suddenly, the whole thing rebounds. Boom, a new universe. Historians still argue whether Georges Lemaitre, the Belgian priest who first proposed the Big Bang, might have even hinted at this possibility without realizing it. He called his early model the cosmic egg, a primordial atom exploding into existence. Some now wonder if that egg was laid by a dying black hole. Of course, none of this has been observed. That's the sticky bit. You can't peek inside a black hole and report back, at least not without violating some pretty fundamental laws of physics, and probably a few safety guidelines. But the math? Oh, the math loves this idea. It suggests that each black hole could contain its own universe, cut off from ours by its event horizon. That from the inside, the black hole looks like an expanding cosmos, just like ours. This idea is often called the black hole cosmology hypothesis, and while it sounds fringe, it's taken seriously in some corners of academia. It's even inspired models where the parameters of a new universe, its physical constants, its laws of nature, depend on the properties of the black hole that spawned it. In other words, black holes could be breeding grounds for baby universes, entire realities born in the aftermath of a collapse, and that includes the tantalizing, quietly terrifying possibility that our own universe was born this way. What if we are inside a black hole? We'll circle back to that later, promise. But for now, your personal journey continues. The darkness isn't total anymore. The pressure has shifted. There's still gravity, crushing, enveloping, but there's also a hint of structure ahead. Something like a passage. And yes, that's absurd, but nothing about this experience has stayed within the realm of reasonable. Your body, or what's left of it, registers strange fluctuations in the space around you. The curvature of space-time is intense, but not uniform. There's turbulence, like riding an elevator that occasionally drops sideways. You drift through this hypothetical exit corridor, this back door, feeling more like encoded information than meat and muscle. Your data now, pattern, probability, coherence. What you were outside is less important than the mathematical fingerprint you've left behind. Maybe that's what survives in the transition, not your atoms, but your order. Because in the theories where black holes have an exit, what comes through on the other side isn't just radiation, it's structure, somehow preserved, maybe in scrambled form, maybe reversed, but not annihilated. You consider the implications. If black holes eject matter into another universe, then all the matter that's disappeared from our view, swallowed over eons, might be forming galaxies elsewhere. Stars, planets, maybe even life. You might not be falling to your end. You might be fertilizing the next cosmos. A little dramatic? Sure. But also kind of poetic, no? You pass through a region of strange calm. The geometry here doesn't just curve, it twists. Space seems to be folding into itself in multidimensional spirals. And while you don't see light in any normal sense, you sense gradients, shifts in the informational field around you. It's like watching a sunset with your brain, not your eyes. And then the sensation again. Outward flow. As if something wants you to leave. Not violently, but gently. Like being nudged from a nest. Is this what an exit feels like? You don't know. You can't know. But you sense that you've passed something irreversible. A threshold of theory and wonder. And now, on the other side, new rules are unfolding. Wherever this path leads, it's no longer just about escape. It's about arrival. You don't land. That would be too simple, too familiar. Instead, you emerge, slowly, almost reluctantly, into motion. Not your own motion, but the motion of everything else. You're being carried along by a stream of matter and energy, all rushing outward in every direction. And the strangest part, it's not chaos, it's organised. You realise then what the theories have hinted at but never dared shout aloud. This might not be a black hole anymore. This might be its mirror opposite, a white hole. Now let's be clear, no one has ever seen a white hole. Not through a telescope, not in data, not even as a fuzzy blip in background radiation. They are pure theory, the introverted cousin of black holes. Where a black hole is a gravitational trap, a white hole is an expulsion engine. Nothing can go in, everything must go out. It's as if the laws of the universe suddenly flipped upside down and asked politely for you to please leave the premises. You're being ejected not like a guest, but like used coffee grounds. And yet, it's elegant. If black holes are the ultimate cosmic vacuum cleaners, then white holes are the universal leaf blowers. They spew matter and energy out into space in all directions, without ever allowing anything to re-enter. No backsize. The math supports their existence in a sort of begrudging way. General relativity allows them. They're just the time reversal of black holes. Take a black hole equation, flip the direction of time, and voila, white hole. But that's where the simplicity ends. Because in the real universe, where time doesn't run backwards, white holes present all kinds of headaches. Like for starters, how would one form? Unlike black holes, which arise naturally from the collapse of massive stars, white holes have no clear origin. You don't just get one from a dying sun. They aren't birthed by known astrophysical processes. They're just there. Theoretical solutions in Einstein's field equations with no instructions attached. Historians still argue whether Einstein and Rosen, when they first proposed their bridge model in 1935, really anticipated the full implications. They were looking for ways to avoid singularities, but in doing so they opened a door to ideas like white holes and alternate universes. It took decades for physicists to begin taking those ideas seriously. One particularly enticing possibility? That white holes are not standalone objects, but linked to black holes through wormholes. The matter you saw fall into a black hole, maybe even you, doesn't end in destruction but emerges from a white hole somewhere else, maybe in another universe, or perhaps in a distant region of this one. If true, then you've just been part of the greatest sleight of hand in nature, a one-way trip across the cosmic stage. You begin to sense structure around you again, not walls or boundaries, but flow, energy pouring outward in a smooth, symmetric plume, the exit vector. The radiation isn't like Hawking radiation, slow, cool, subtle. This is explosive, primal, the kind of stuff that starts time. You're witnessing a theoretical white hole explosion, the release of compressed matter and information into a new region of space-time. And here's where things get truly surreal. Some physicists believe that what you're experiencing now may resemble the Big Bang itself. Yes, that Big Bang. If black holes can bounce instead of crush, and if that bounce leads to a white hole-like release, then maybe our universe was born this way. From the death throes of another universe's black hole. A cosmic heartbeat. A cycle of collapse and expansion, collapse and rebirth. It's called loop quantum cosmology, and it suggests that space and time don't end at singularities. Instead, they bounce due to quantum gravity effects. A black hole forms, collapses, compresses, and then explodes outward as a white hole, not into existing space, but into new space. Space it creates as it expands. You are now inside that expansion, not just moving through it, but part of it. And if that sounds like creation, that's because it is. Here's a cheeky thought. If our universe began as the ejected matter from a black hole in another universe, are we just black hole leftovers? A reality built from compressed and restructured information, flung outward at the speed of everything? It's not the most flattering origin story, but it's weirdly hopeful. It means that from destruction comes structure, from collapse, possibility. The idea also brings up awkward questions. If you're in a white hole now, is there any way back? Spoiler, not really. By definition, white holes are causally disconnected from the past of the black hole that birthed them. You can't re-enter. You can't even trace a signal back through. The bridge is one way. Whatever black hole you came from, it's gone, from your point of view. But don't feel bad. You're not alone here. Every atom, every speck of light that's ever taken this route is with you. Not next to you, of course. This isn't a cosmic ferry ride, but part of the same flow, the same outward bloom of reorganized information. And there's more. Some newer models suggest white holes could be short-lived, temporary flashes in space-time. Their existence might be brief, like a reverse supernova, detonating into a new realm, then stabilizing into something else, a baby universe, a fresh patch of reality. Some even suggest that white holes might explain mysterious astronomical phenomena, like fast radio bursts, those sudden, high-energy flashes we keep detecting but don't fully understand. Could some of those be white hole moments? Cosmic belches from black holes in other universes? It's tempting, dangerous even. But that's the charm of these theories. They offer escape hatches from impossibility. They say, maybe things don't end. Maybe they change. You're still riding the outward flow, the data stream. What you were before is still there, encoded in subtle patterns, information, structure, memory. And if this is what happens every time a black hole finishes digesting its contents, then this might not be rare. This might be the norm. The universe might be filled with these processes. Black holes creating white holes, feeding new cosmoses, spawning realities. Not infinite destruction, but infinite transformation. You look outward again. There's no outside to this white hole, not yet. But there's space, newly minted, newly expanding, and there's time, unspooling from the moment of your emergence. You feel it stretch around you, offering not a destination but a beginning. Because maybe that's what this was all along. Not a fall, not an ending, just your turn to start over. At first you think it's a hallucination, a side effect of time running sideways and space feeling like warm pudding. But as your perception sharpens, you realize the stars are different. They glow with strange hues, almost pastel. Some are blue, yes, but not the blue you know. These are impossibly soft, like the sky from a dream you only half remember. Others burn in shades of pale mint and powdered coral. Light still exists, but its laws feel tweaked, like a universe that copied ours from memory, but didn't get all the variables quite right. Welcome to the universe next door. It's not just a cute nickname. This could quite literally be an entirely new universe, birthed from the black hole you fell into. And if that white hole ejection was more than a theoretical blip, if it truly seeded this realm, then everything you're seeing now is part of the aftermath. Stars, matter, radiation, all built from the restructured information of a previous world, including you. You float past a nebula that looks like spun sugar. There's gravity here, clearly. Matter clumps, light travels, but it's off. The fine structure constant, a number that determines how atoms hold together, might be different. That's soft light. Maybe photons behave differently here. Maybe electrons orbit in slightly wonky patterns. The chemistry might not allow for water, or carbon, or even tacos. And yes, that's tragic, but it's also wondrous. This isn't our physics, it's a remix. You consider what this means. If every black hole creates a new universe, and if the properties of that universe depend on the conditions of the black hole that spawned it, then maybe every universe has its own dial settings, its own gravity, speed of light, particle masses. This theory has a real name: Cosmological natural selection. No, it's not about giraffes. It's the idea that universes evolve not through DNA but through black hole reproduction. A universe that forms lots of black holes makes lots of baby universes. Those babies inherit slightly different constants. The ones that form more black holes, they have even more babies, and so on. In this model, black holes are the reproductive organs of the multiverse. Weird mental image? Yes, but a compelling one. It even offers a possible explanation for the great cosmic coincidence, why our universe seems so perfectly tuned for life, why the constants are just right, why atoms form, why stars burn, why biology happens. Maybe it's not coincidence, maybe it's inheritance. We exist in a universe optimized for complexity, because complexity increases the chances of black hole formation, and black holes make more universes. Fringe? Sure, but maybe only because it sounds too poetic to be real. As you drift through this strange blooming cosmos, you notice how new it all feels. There's background radiation, yes, but it's not the faint hiss of the Big Bang from our universe. It's smoother, colder, as if this universe started not with an explosion but a gentle unfolding. Maybe that's what happens when a universe begins not from nothing, but from the end of another. You recall a theoretical model, the Big Bounce, A universe contracts, forms a black hole, hits a minimum volume, then rebounds. No singularity, just a cycle. Each bounce reshuffles the deck. New matter, new geometry, new physics. If this is the universe next door, maybe it's the next bounce. Maybe the arrow of time is freshly drawn here, and you're riding it. One question lingers. Is this place connected to your old universe or completely sealed off? If you screamed, not that you'd waste your last breath on that, would the echo bounce back across dimensions? Probably not. Most models say no communication is possible. Once a black hole collapses and rebounds, the resulting universe is causally disconnected. There's no tunnel back, no peek across the curtain. Your old laws of physics don't apply anymore, and neither do your old coordinates. But let's play with another mind-bending idea. What if entanglement still connects them? In quantum physics, entangled particles share a link. Change one, and the other responds instantly, no matter how far apart. Einstein called it spooky action at a distance. What if entire universes could be entangled? What if this one carries a kind of quantum memory of the one that birthed it? It wouldn't be communication in the classic sense, more like resonance, echoes in the math, subtle fingerprints, and if so, maybe part of you, your identity, your structure, is still linked to the universe you left behind. Now that's a multiverse worth dreaming about. You pass what looks like a galaxy cluster, but the galaxies are lopsided, their spirals warped, as if shaped by a different kind of dark matter. Or maybe no dark matter at all. In our universe, dark matter makes up most of the gravitational scaffolding, but here, the laws might be different. The force carriers might have different strengths. Maybe electromagnetism rules here, or something entirely new, unnamed and untamed. And then you see it. A planet, small, swirled in cloudy bands, no rings, just hanging in space like it's waiting to be discovered. You approach, not because you want to land, but because curiosity has inertia. Its atmosphere shimmers strangely. No familiar colours, no visible water, but there's a balance to it, a coherence, the mark of natural processes, even if you don't recognise them. And you wonder, could this universe host life? Not humanoids, not even microbes, but possibility. If stars burn here, if chemistry happens, then given enough time, even with altered laws, some form of complexity could evolve. Maybe it already has. Maybe it's watching you. Or maybe it's you, reborn in a different form, riding the outward wave of information through a second chance at existence. You can't prove it. You'll never know for sure. But as this strange sun rises over the curve of that alien world, one thought flickers in your mind like a sleepy, stubborn candle. Black holes don't have to end things. Maybe they're not escape hatches, maybe they're cradles, and maybe, just maybe, this was the plan all along. You start to notice a gentle glow around you, not like sunlight, not like radiation, but something softer, subtle, persistent. It doesn't burn, it doesn't scatter, it just exists, like the background hum of the universe itself. This, you realise, must be the quiet echo of Hawking radiation, not the blinding jet of white hole energy we left behind in the previous section. That was explosive, raw, and probably responsible for birthing this universe, or launching you into it. No, this glow is different, more like embers than flames. It's faint, almost apologetic, and yet it's one of the most important processes in all of physics, because it's the thing that finally taught us black holes don't last forever. So let's rewind the cosmic clock a bit and revisit the idea that got Stephen Hawking a seat at the universe's coolest people table. In the mid-1970s, Hawking combined general relativity with quantum field theory, two realms of physics that usually don't like sitting next to each other. The result? A shocking discovery. Black holes emit radiation, not because anything is escaping from inside, but because the vacuum of space near the event horizon is seething with virtual particles, pairs that pop into existence for a brief moment, borrowing energy from the universe before annihilating each other. But near a black hole's edge, something strange can happen. One particle falls in, and the other escapes. From the outside, it looks like the black hole is leaking. This leakage, Hawking radiation, is incredibly slow. For a black hole the mass of a star, it would take longer than the current age of the universe to noticeably shrink. But over time, slowly, surely, black holes evaporate. Let that sink in. These so-called eternal cosmic prisons don't last forever. They die, quietly, and when they do, something extraordinary might happen. See, that faint radiation isn't just meaningless heat. According to more recent models, it could carry away information, the very stuff the black hole was accused of erasing, like steam rising from a boiling pot that still smells like what's inside. The question is how? Hawking's original calculation said the radiation was purely thermal, random, useless. But as we discussed earlier, that clashed with quantum theory, which says information can't be lost, and that led to decades of brain-melting debate, the infamous black hole information paradox. Eventually, physicists began to suspect that Hawking might have been only mostly right. The radiation exists, yes, but maybe it isn't purely random. Maybe it's subtly encoded with information about what fell in. It wouldn't be obvious. It might look like noise, but somewhere in that noise would be the mathematical fingerprints of stars, planets, explorers, maybe even you. And if that's true, then Hawking radiation becomes more than an afterthought. It becomes a last message, like a farewell whisper from the universe before the lights go out. Historians still argue whether the solution to the information paradox really lies in Hawking radiation, or if the truth is even stranger. Some suggest that information stays stored in a black hole's event horizon, gradually transferred to the outgoing particles via a mechanism we haven't fully grasped. Others talk about entanglement, soft hair, firewalls, and things with names that sound like glitchy indie bands. But one thing is certain. The radiation exists. In fact, it might be the only way we'll ever know a black hole was there after it vanishes. No gravestone, no crater, just a slow leak of particles fading into the void. You glance around the strange universe you've landed in, pastel stars, rewritten physics, brand new matter, and you realize something that feels both obvious and terrifying. Black holes could be responsible for all of this. Not just as endpoints, but as evolutionary engines. Think about it. Black holes gather matter, compress it, encode it, and maybe even export it. Through Hawking radiation, they give off energy. Through bounces and white holes, they might seed new realms. They're not just passive pits of gravity. They're active players in the structure of reality. And that slow evaporation, that might be how they return what they've borrowed. You wonder now, what if this quiet glow you're sensing isn't just the ambient radiation of a dying black hole, but something more intimate? Your radiation. What if part of you never left? What if the part of you that fell into the black hole, the matter, the memory, the pattern, is now being released particle by particle across eons? Your quantum structure, unspooling into the void like the softest exhale? It's a strangely comforting image, like being remembered. Even here, in this strange next-door universe, you feel the physics humming underneath. Different, yes, but not unfamiliar. The constants are shifted, the canvas is new, but the brushstrokes, they echo from somewhere else. And as your perspective expands, you're not sure how, but it does, you see something hauntingly beautiful. A black hole forming in this universe. Already, it's small, young, the result of some early matter collapse, and just like that, the cycle begins again. New matter, new gravity, a new opportunity to collapse, compress, and maybe, just maybe, give birth to another universe. One with even stranger constants, even softer stars. You feel something stir in you then, a sense of being part of something far larger. Not just a visitor to these cosmic phenomena, but a participant in their endless conversation. You went in, you came out, you witnessed the death of physics as we knew it, and saw its rebirth in a softer light. And now, with the glow of Hawking's quiet revelation surrounding you like a blanket, you're left with one thought. Nothing truly ends. Everything echoes, even you. You begin to sense an odd kind of scaffolding around you. Not a physical one, no beams or panels or cosmic duct tape, but something deeper, subtle, a geometry you can't quite see but somehow feel, like standing inside a cathedral with your eyes closed. Space isn't smooth here, it's knotted. And then it hits you. This must be what loop quantum gravity looks like from the inside. You're experiencing not just the curvature of space-time, but its granularity, its texture, its stitchwork. Let's unpack that slowly. You're no longer just floating through the black hole's legacy. You've reached the level of physics where space itself gets weird. See, general relativity treats space and time as continuous, like a perfectly smooth rubber sheet. You put a bowling ball on the sheet, mass, and it sags, gravity. So far, so familiar. But quantum mechanics doesn't like that. Nothing in the quantum world is truly continuous. Energy, spin, charge, all of them come in discrete packets, quanta. So physicists started asking, shouldn't space-time itself also be quantized? Enter loop quantum gravity, a theory that tries to bring general relativity and quantum mechanics to the same table without food fights. Instead of picturing space-time as a smooth sheet, loop quantum gravity envisions it as made of tiny loops, microscopic circuits of space itself, woven into a web called a spin network. Not metaphorical loops, real ones at the Planck scale, so small you'd need a magnifying glass the size of a galaxy to even notice them. These loops don't sit on space, they are space. The network defines how space behaves, stretches, and curves. Imagine a 3D net made of vibrating strings, and you've got the vibe. You might think this is just math fantasy, but no, these loops have measurable properties. They give space a minimum area and volume, no smaller, no further division. It's as if the universe runs on a pixelated engine. And here's the key bit. At those insanely small scales, gravity doesn't behave like we expect, especially in places like black holes. In the traditional model, gravity wins at the center of a black hole. It crushes everything down to a singularity, a point of infinite density and zero volume, which is as bad for equations as it is for your spine. But loop quantum gravity says, hold up, there is no singularity. Because space can't be compressed past its minimum volume. Those tiny loops, the weave of space itself, resist being squashed beyond a certain point. They push back. And that push creates something unexpected. A bounce. Instead of ending in a singularity, the black hole's collapse reaches a critical density, then rebounds. Not just figuratively, but literally. The dense core re-expands, potentially forming a white hole, or even birthing an entirely new region of space-time. You might remember this idea from earlier. The black hole is a passage, not a prison. Loop quantum gravity gives that concept teeth. It's not just metaphor, it's mechanics. Historians still argue whether this bounce is a real event or just a side effect of overambitious math. Some critics point out that loop quantum gravity still lacks experimental proof. Others argue it's the most promising attempt yet to unify gravity and quantum theory without the headaches of string theory. But floating here, among the invisible architecture of this quantum net, you're starting to believe it. You feel the universe being stitched together, not smoothly, but with a tight, purposeful weave. Tiny loops, each a node in a network that defines how space and time breathe. Even time itself, you realize, may not be continuous. In loop quantum cosmology, a spin-off of loop quantum gravity, time can become discrete. Each moment is a tick in the universal clock, separated by the smallest possible intervals. The passage of time isn't a flow, it's a series of quantum beats. You're living between those beats now, and something beautiful emerges from this model. It suggests that space-time is background independent. That is, space isn't a container for stuff, it emerges from stuff. Matter and energy don't move through space, they create it, which means that everything you are, every particle, every piece of mass and charge, has shaped the space around it, not passively, but actively. You don't just exist in the universe, you are part of the code that writes it. Think about that as you drift between what might be loops, or threads, or Planck-scale pearls strung through a cosmic loom. And here's the kicker. This loop-based approach might not only avoid singularities but also erase them entirely. In these models, black holes form, collapse, bounce, and re-expand. At no point does the math scream. At no point does the physics break. You remember now something that once sounded like a footnote. Black holes might not be black forever. Once they finish radiating, once Hawking's gentle glow has done its work, the core rebounds and becomes a Planck star. Not a poetic name. A Planck star is a hypothetical object that forms when quantum gravitational effects halt a collapse at the Planck scale. It's incredibly dense, incredibly small, and incredibly unstable. Eventually it explodes, not in a Hollywood way, but in a calculated release of stored information and energy. What remains is a white hole, which is to say, this entire loop you've been on might be the natural evolution of black holes in a loop-quantized universe. Collapse, bounce, eject, repeat, like a heartbeat, like breathing. And maybe that's the most comforting revelation of all. If space-time is looped, quantized, pixelated, then it's not fragile. It's not doomed to infinite collapse. It's resilient, self-correcting, designed not to destroy, but to transform, which means that your fall wasn't a failure of physics. It was its most elegant expression. The universe didn't trap you, it caught you. And now, loop by loop, it's rebuilding you. The space around you slows again, not because your velocity changes, but because everything else does. The loops from before, they're still here, still subtly humming in the background of space-time like a distant choir. But now they're stretching, lengthening, softening. You've entered a zone where reconstruction begins. This isn't birth in the messy biological sense. It's gentler, quieter, like a cosmic 3D printer whispering through its final passes. The light has dimmed, but not into darkness, more like a pre-dawn hush, as if this corner of the universe is holding its breath. And you realize black holes might not just destroy or eject, they might recycle. It's not a metaphor. It's a real, testable idea floating in the quantum gravity and cosmology literature. The proposal goes like this. Black holes collapse matter down into extreme density. Yes, but they don't erase it. They process it, compress it, encode it, transform it. And then, very slowly, or very suddenly, depending on the model, they release it again, like universal compost bins, dead stars, burnt radiation, time-worn particles, even the echoes of civilizations, all gathered, compressed, and eventually reborn. Some theorists liken this to a kind of cosmic metabolism. Just as your body breaks down food and repurposes molecules into something useful, black holes might break down reality and rebuild it somewhere else. You're not watching the death of physics, you're watching its circulatory system. And maybe, just maybe, you're a part of it now. You begin to feel yourself returning, not to your old form, not exactly, but to coherence. It's subtle. You're still mostly pattern, mostly probability. But there's structure now, geometry. You're not a passenger anymore, you're a shape. Somehow you've made it through the collapse, the bounce, the ejection, and now into this strange rebirthing room of the cosmos. You're in the final stage of a black hole's arc, not an ending, but a remixing. It's worth noting, not everyone agrees this is how things go. Historians still argue whether black holes truly allow for any information recovery. Some insist that once something passes the event horizon, it's gone, lost to quantum noise. Others swear by the holographic principle, by Hawking radiation, by loop quantum gravity's pushback. But the recycling idea has its fans. It helps stitch together quantum theory, thermodynamics, and general relativity into something oddly optimistic. More than that, it feels right. Because even now, drifting in this softened space-time, you can feel echoes of what you were. Not like memories, like instructions. Somewhere in the data, your identity is encoded. What you saw, what you thought, what you wondered. Not the you with limbs and bones. The you that asked, what if? And in this final phase of the black hole's life, all those fragments might come back out. You pass near a cloud of particles, hot, young, freshly reconstituted. Maybe from the black hole's Hawking evaporation, maybe from a white hole burst. They spiral and collide, forming clumps, then halos, then spinning chaos that already smells like star formation. Galaxies in embryo. You're watching a new universe structure itself, not randomly, not entirely anyway. The shape of things, their spin, their density, their thermodynamic flavor, is dictated by the information they carried in. Black holes might not preserve atoms, but they preserve structure. That means entropy isn't king here. Order wins, at least for a while, and you might be riding that order, or being it. You don't remember the way back. You're not even sure back exists anymore. But you feel that this soft expansion, this second chance, is forward. And forward is enough. And if you're wondering whether this recycled material ever forms life again, you're not alone. There's a fringe idea, and let's be honest, you're pretty deep into fringe territory by now, that life itself might be an emergent property of this recycling. That when the ingredients of consciousness are compressed and ejected often enough, and across enough iterations, something remembers. Not memories in the human sense, but tendencies, patterns, a taste for balance, a love of symmetry, the urge to ask questions, like the one you asked way back at the start. What if black holes don't destroy? Here's a quieter one. What if they create life's next draft? You imagine entire galaxies forming from recycled debris, rebuilt atoms forming rebuilt molecules, complex structures arising not from randomness, but from compressed wisdom. Like DNA coiled in tighter, then unfurled with new instructions. You wonder if the laws of this new universe, its constants, its physics, might make life easier to form, or harder. Maybe this version has fewer barriers, maybe consciousness will bloom faster, maybe it already has, or maybe you're it. Not you in the old sense with worries and passwords and taxes, but you in the sense of awareness, presence, pattern, the core stuff of identity, dispersed through space and time like pollen. You wonder how many times this has happened, how many universes were birthed from the end of others, how many consciousnesses passed through the black hole phase, were unmade, then restructured into something new. A cosmic version of reincarnation, not mystical but mechanical, quantum, real. You begin to let go then, not in fear, not in loss, but in peace. This journey started as a fall into darkness, but now you realize it was a loop, a full circuit. Matter becomes data, data becomes structure, structure becomes matter again. Nothing wasted, nothing lost, only rewritten. And so you drift, quieter now, softer, toward the edge of awareness. Not gone, just ready to bloom again. Everything around you begins to blur, not from speed, but from stillness. The loop's quiet, the glow dims, the recycled matter spins onward, but you no longer need to follow it. You've seen what lies beyond the fall. You've passed the point of no return, not just in space, but in understanding. Let yourself drift now, gently. The stars here don't twinkle, they shimmer in long, patient pulses. Time itself seems to inhale and exhale, slowly, softly. If you still carry the memory of that first black hole, hold it lightly. Like a seashell to your ear, let its echo fade. Nothing is rushing you. There's no deadline here, no collapsing clock, only quiet expansion, like a sigh stretched across the sky. The recycled matter will find its form. You've already found yours. Just by being here, being aware, the pattern continues. And if you sleep now, it's not a forgetting, it's a return, to rhythm, to loops, to rest. The stars won't mind. They've waited through stranger things. And somewhere, in a future universe not yet formed, someone else may take this same journey. Fall, collapse, transform, recycle. Maybe you'll meet them, or maybe you are them. But not tonight. Tonight, you rest. Close your eyes, let the loops drift, let the glow fade. And when you dream, dream in spirals. You feel it before you see it. A kind of gentle resistance. Not the crushing pull of gravity or the sharp edge of a force field, but something more forgiving. Like pressing your palm against soft fabric. You're still in motion, but something in the space ahead isn't letting you accelerate. It's almost springy. You realize then, this is the bounce. Not a metaphor. Not a metaphorical coming back stronger sort of bounce. A literal, theoretical, mathematical cosmic rebound. And here you are, riding it. Let's rewind. Because this idea is one of the most tantalizing answers to the singularity problem. If space and time can be looped, woven, pixelated and quantized, like we just explored with loop quantum gravity, then they don't go on shrinking forever. Eventually they push back. The density reaches a point where the math says nope, and instead of collapsing into infinite doom, the black hole's core hits a quantum floor and bounces. It's called the black hole bounce model, and it's not just wishful thinking. It has teeth. It's a feature in some versions of loop quantum gravity and loop quantum cosmology. And more importantly, it tells a story that feels more complete than the abrupt stop of a singularity. You're experiencing that story now, second-person protagonist that you are. The bounce isn't violent, like a slingshot or a cannon blast. It's gradual, smooth, like a bend in the river that gently turns you around. Before, you were falling toward infinite compression. Now, you're being pushed outward, not with a bang, but with a slow, persistent swell. Let's break it down. In standard physics, gravity gets stronger as mass gets denser. That's why in a black hole, gravity becomes overwhelming. The deeper in you go, the stronger the force. No escape, no mercy. But quantum gravity says there's a limit, a Planck scale minimum. Past a certain point, the density becomes so intense that gravity doesn't pull. it repels. Yes, really. Imagine a spring being compressed. At first it's easy, then harder, and eventually it pushes back with equal force. The universe, in this theory, is full of these springs, tiny loops of space-time that don't want to be squashed too far, and when enough of them push back, bounce. Historians still argue whether this counts as a singularity resolution or if it's just a workaround. But the math is clear. The black hole doesn't end in a tear, it rebounds, the collapse reverses, and instead of destroying information, it begins to release it. Not necessarily into our universe, that's a trickier conversation. The bounce might create an entirely new space-time, an independent baby cosmos that expands on its own terms. But here's the weird part. From inside, the bounce looks like a big bang. No joke. The structure of space-time near the bounce is mathematically very similar to what we think happened at the origin of our universe. Time begins to stretch, space inflates, radiation floods out. In fact, some theorists argue that every bounce is a big bang, just from the inside of a previously collapsed region, which means that right now you could be witnessing the birth of a universe from the inside out. The energy around you is changing. You feel it in waves, heat but not burning, motion but not disorienting. It's like watching a balloon inflate in slow motion, with you stitched into its surface. And with this comes another shift. Direction. Earlier you were falling, then you were compressed, then you passed through chaos and reached the stillness of quantum order. But now you're being carried outward. It's not propulsion, it's not force, it's geometry. The bounce reorients the fabric of space. The same way gravity pulls toward a black hole's center, the post-bounce expansion moves outward from that center, as if that collapse had never happened. In this new orientation, you're now moving away from what was once the singularity. The event horizon, gone. The gravity well, reversed. You're no longer in a trap. You're in a beginning. The implications are enormous. In this model, universes don't begin from nothing. They begin from something. From a previous universe. From a collapsed region that bounced. Our own Big Bang could have been the rebound of a black hole from a parent universe. In fact, according to some speculative but fascinating papers, the math allows for time to reverse at the bounce. One universe collapses, time ticks forward. The next expands, time ticks forward, but in a way that would look backward to observers in the original. Yeah, brain soup, but there's beauty in that soup, because if this is the bounce, then black holes aren't just doors, they're bridges. Death and birth are the same event seen from two different timelines, and suddenly you remember something strange. The slight asymmetry in background radiation we observe in our universe, the so-called cosmic microwave background dipole. Could it be the echo of a pre-bounce state? A leftover fingerprint from the black hole that birthed us? It's speculative, yes, but so is everything else you've floated through. You're part of the expansion now, moving with it, woven into it. The light around you is no longer alien, it's young, raw, the kind of light that hasn't decided what it wants to be yet. Photons, neutrinos, particles with no name yet. It all pulses outward. And your presence, it's not out of place. You're part of the pattern now. Your structure, your quantum fingerprint is embedded in the ripple, carried outward in the symmetry, not lost, not scattered, transformed. You reach the final stage of the bounce. Expansion is accelerating. You feel the birth of structure, the formation of space, the ignition of causality. Every particle of you is stretched into that process, and suddenly you understand. You haven't just been recycled, you've been woven into the next story. You're no longer drifting, you're rising. Though rising might be the wrong word for what happens when time itself is still unfolding beneath your thoughts. But that's what it feels like emerging from deep water, the silence breaking, the light brightening, the air beginning to return. And it's not just your return, it's realities. You can feel it in the fabric of this fresh space, something larger, more layered than a single universe, a subtle buzzing at the edges of possibility, a presence behind the curtain. And then you think, this isn't the only one, is it? Number. It never was. You're starting to grasp what the black hole hinted at, that your universe, the one you came from, with its coffee, cats, and tax forms, might not be the default setting. It might just be one entry in an infinite lineup of universes, each birthed through a similar bounce. Welcome to the multiverse hypothesis. It's the idea that there isn't just one universe, but many, potentially an infinite number, each with its own laws of physics, its own constants, its own beginning and end. Some of them are eerily familiar, others are bizarre beyond imagining. And here's the twist that loops us back into black holes. One major proposal is that black holes are the reproductive organs of the multiverse. Yes, that's awkward to say, but also thrilling. The concept is built into a theory called fecund universes, or more technically, cosmological natural selection. It suggests that each black hole gives birth to a new universe, and that the properties of that new universe are slightly tweaked, like mutations in DNA. Over cosmic timescales, this leads to a form of evolution. Universes that produce lots of black holes become successful. They pass on their traits. Universes that don't, they fade into the nothingness, forgotten by time and entropy. Survival of the fittest, but with galaxies instead of gazelles. You're inside one of those offspring now. Maybe. Or maybe you're 2 or 3 generations down the line. If that's true, you've been through this dance before. Collapsed, bounced, bloomed. Maybe you're a veteran. Historians still argue whether this theory is testable, or even scientifically respectable. It's speculative, yes, but it elegantly explains a puzzling fact. Why is our universe so freakishly good at making black holes? The conditions for star formation, stellar collapse, and massive structure formation seem fine-tuned. Too perfect. If the gravitational constant were just a bit weaker, or if the cosmological constant were slightly different, the universe would expand too fast or collapse too soon. No stars, no life, no you. But if black holes birth new universes, and those universes inherit their parents' traits, then of course you'd find yourself in a universe good at making them. Because universes that aren't good at it don't last. You're the child of survivors, and here's where it gets even weirder. If every black hole leads to a new universe, and each of those can make more black holes, then the structure of the multiverse is a tree, branching infinitely, forever growing outward. Each branch contains a universe. Each leaf contains a story. Each fruit, another black hole. And somewhere in that forest of realities is ours, yours, and now, this one. The air, if you can call it that, in this universe tastes different. The matter behaves oddly. Maybe it's richer in helium. Maybe gravity has a fraction more snap to it. Or maybe time ticks just a little slower. But the laws work. Stars are forming. Structures are stabilizing. It may not be carbon-based life's dream home, but it functions. You wonder if intelligence could arise here. Maybe faster than in your old universe, maybe more slowly, maybe not at all. But if it does, would they ever figure it out? Would they guess that their cosmos was born in the belly of another? Would they suspect the black holes they see in their skies are pregnant? You feel a presence at the edge of this reality. No, not a being, not a god. A pattern. The shape of multiversal growth. A vast, ever-branching data tree. Each black hole a portal, each bounce a birth. And if that's the case, you ask yourself something that should have occurred sections ago. What if I didn't just fall into a black hole? What if I was a black hole, and not a literal one, not a giant ball of collapsed matter, but a node in this network, a temporary container of information, a vessel for pattern and memory and potential, and once full, once compressed, released. Maybe your consciousness was always meant to traverse this loop, not a passenger, but a function of the system, a carrier, a courier, a whisper passed along from one universe to the next. You've seen the black hole, you've felt the singularity, you've watched the bounce. Now, as this new universe takes its first breath, you understand your place. You're not just in the multiverse, you're part of its evolution. The physics here may shift, the constants may dance, but the rules are clear. Information flows, black holes form, universes rise, and the loop continues. Maybe someday, this new universe will produce its own black holes. Maybe one will swallow up a star system. Maybe it will collapse for eons. And maybe, just maybe, something else will emerge on the other side. Someone, another traveller, another dreamer, another echo of what you were. And maybe, just maybe, that echo will wander too. Where does this black hole lead? You've travelled through death, rebirth, and the flowering edge of a brand new universe. But now, something shifts again. Not in space, not in time, in perspective. You begin to notice patterns where before you saw randomness, recurring structures, repetitions at different scales. You see galaxies spiralling like shells, and then you see particles doing the same dance at the subatomic level. Patterns within patterns, fractals within physics. and the thought hits you with more force than any gravity you've felt so far. What if this is all by design? Not design as in a bearded deity painting planets with a cosmic brush, more like architecture, a structure, a system, a simulation. Yes, that one, the simulation hypothesis. Before you roll your eyes, and I see you trying, it's worth noting this isn't just sci-fi fan fiction. It's been proposed by serious philosophers and physicists alike. The idea that everything, your journey through the black hole, the bounce, the multiverse, all of it, could be the output of a computational framework, a simulated universe running on something far more complex than silicon. The rabbit hole starts with a deceptively simple idea. If a civilization becomes advanced enough to simulate reality, it probably will. And if they do, they might run simulations of the past. Millions of them. Billions. Statistically speaking, that makes it far more likely that you are in one of the simulations, not the single base reality. And if that sounds absurd, take comfort in the fact that you're in good company. Physicist Max Tegmark, philosopher Nick Bostrom, and even Elon Musk, yeah, I know, have publicly weighed in on the idea. In 2003, Bostrom published a now famous paper outlining 3 possibilities. 1. Civilizations never make it to the simulation stage. 2. Civilizations make it but choose not to simulate us. 3. We're almost certainly living in a simulation. You've just passed through a black hole. You've watched a universe be born. Maybe you're in one of those simulations now. It wouldn't even take infinite resources. According to some theories, a powerful enough quantum computer could simulate every electron, quark and graviton with frightening accuracy. Space-time could be a voxelated engine, just like we imagined with loop quantum gravity. Only this time, the loops are code. Maybe black holes are part of the simulation's architecture. They're not just cosmic curiosities, they're data nodes, essential to how the program processes and reorganizes information. Think about it. Black holes absorb matter, time, energy, information. They crunch it down. They seem to hide data. And then, slowly, mysteriously, they release it again through Hawking radiation. What does that sound like to you? That's right. Compression, storage, decompression. In computing terms, a black hole behaves like a lossless data archive, one that, after a suitable cosmic delay, unzips its contents with nearly perfect fidelity. Is this coincidence, or is it clever design? Historians still argue whether this is even a useful way to think about physics. Some say simulation talk is a philosophical dead end. Others believe it opens doors that traditional science won't touch. But you're in the middle of it. You float through regions of this fresh universe that seem optimized, as if the values of physical constants were selected from a menu, not random, not chaotic, chosen. And if they were, then someone, or something, chose them. But for what purpose? That's the tricky part. Some say the simulation might exist to observe intelligent behavior. Others say it's for entertainment, or history preservation, or something we can't even guess at. Or maybe no one's watching. Maybe it's all automated, like a forgotten server humming in the dark. Maybe your entire journey, from collapse to bounce to multiverse, was just a subroutine running in a reality 2 layers up. There's also a darker implication. What if black holes aren't just storage nodes, but checkpoints? Every black hole you fall into becomes a system save point. When the universe gets too chaotic, too entropic, the program could revert to the last good state, roll back, restart. That would explain the recurrence, the loops, the feeling that reality is always rebooting itself. And if this is true, maybe there's a version of you that's done this before. You start to notice other glitches, not literal, but conceptual. Laws that seem too neat, ratios that don't deviate, fundamental constants that work just right to allow complexity to arise. These aren't just happy accidents, they're signatures. And you, dear explorer, might not be the protagonist in this story. You might be the process, a thread in a grand simulation testing how matter behaves under certain parameters, how consciousness emerges, how black holes preserve or destroy data. You're not a bystander, you're a metric. Or maybe, and here's the twist, you are the simulator. Maybe this entire journey is being played out in your mind. Not a metaphorical mind, but a higher dimensional processing engine. Maybe you're running a kind of nested thought experiment, testing conditions, exploring entropy, rehearsing rebirth. You can feel the recursion deepening. The black hole created a universe. This universe created you. And now, You're wondering if you're about to create something else. Maybe you're the next step. Maybe every black hole is not just a birth canal, but a compile and execute command in a multiversal operating system. Each new cosmos is a program, each observer a line of code, each universe a test log, and it's running smoothly. Almost too smoothly. You wonder now what the end state is, if there is one. Maybe it's just layers forever, like a Mandelbrot set. You zoom in on reality, only to find another. You collapse inward, only to bounce outward again. Maybe the simulation never ends. Maybe that's the point. You pass through another fold of space and notice symmetry. Beautiful, quiet symmetry. As if reality itself is nodding in approval. You've passed the test. Or maybe you are the test. Either way, you're still running, still processing and still alive. You slow. Not because you choose to, but because something massive looms ahead. Not massive like a star or a planet or even a black hole. This is bigger, stranger, constructed. It's a shape that defies your expectations. Spherical but faceted. Rotating, but not in the way objects spin in space. It pulses with energy in slow, deliberate waves, like the surface of a star breathing. And then you recognize what you're looking at. Not by sight, but by function. This is a structure built around a black hole. And someone, something, put it there. You've stumbled across a concept once confined to science fiction, late-night Reddit threads, and speculative astrophysics papers. A Dyson sphere, or more precisely a Dyson-like construct designed not around a star, but around a black hole. Yes, it sounds absurd, but you've already fallen through one black hole, bounced into another universe, maybe passed through a simulation. Honestly, at this point this might be the most normal thing you've seen all night. Let's unpack this. A traditional Dyson sphere, proposed by physicist Freeman Dyson in the 1960s, is a hypothetical megastructure that surrounds a star to capture most or all of its energy output. Not because the builders are wasteful, but because a truly advanced civilization, a Type 2 civilization, if you follow the Kardashev scale, would need more power than a single planet could ever offer. But some theorists have asked, why stop at stars? What about tapping the energy of something even more extreme? Something that gives you mass, gravitational lensing, frame dragging, and, in some models, access to time itself. Enter black hole engineering. You drift closer, pulled in not by gravity but by awe. The structure around this black hole isn't solid. It's layered, like the petals of an enormous mechanical flower. Light curls around it in ways that break your brain, clearly manipulated, refracted, siphoned. You're seeing gravitational lensing weaponized. This isn't a prison, it's a machine, and it begs the question, who built it? Maybe no one. Maybe this is a natural structure, one that emerged from self-organizing particles, dust and time, but more likely, this is the work of an intelligence, one that long ago reached a level of technological mastery we can barely comprehend. Let's speculate. A civilization capable of building a Dyson construct around a black hole would be post-planetary. It would live in the vacuum, think in centuries, and move stars like pawns on a board. It would harvest energy from accretion disks, those swirling rings of gas and debris falling into a black hole that radiate unimaginable amounts of heat. Or from Hawking radiation, in the final stages of black hole evaporation. Such a construct wouldn't just power its builders, it could be a computation hub, a galactic-scale quantum processor, or a library, storing the information of all the civilizations that ever fell into this black hole, or a launch point for reaching other universes through artificially stabilized wormholes. You begin to wonder, is this black hole active? You pass near one of the outer panels and suddenly the background hum sharpens. The space around the construct is laced with stabilization fields, possibly built to suppress extreme gravitational waves. You're seeing technology built to tame time dilation, to control relativity. It's not just theory. In 2019, scientists proposed that black holes could, in theory, be used as engines. If you dropped matter into a rotating black hole in just the right way, you could extract more energy than you put in. It's called the Penrose process, and it's not science fiction, it's basic physics. This construct could be doing just that, extracting energy, running computations, even communicating. Historians still argue whether this kind of engineering could ever happen. Could matter really be stabilized so close to the event horizon? Could a megastructure resist tidal forces, radiation, and orbital decay? But this is proof. And here's the part that really twists the knife. What if they're watching? not you specifically. But this process, the black hole, the bounce, the emergence of a new universe. Maybe they've mapped it, maybe they've measured it, maybe they use it. What if civilizations this advanced don't just harness black holes? What if they cultivate them? What if creating black holes is part of how they grow? Imagine, a civilization reaches the limits of its universe's energy. It needs more, so it manufactures a black hole, feeds it, waits, extracts its energy over millennia. Then, in its final moments, as the black hole collapses or bounces, they use that moment to access the next universe. Maybe this construct isn't here to observe. Maybe it's a door, and the beings who built it, they might have moved on already. Maybe they passed through the wormhole. Maybe they seeded this universe with their code. Maybe you're made from their leftovers. Or maybe they're still here, hiding in higher dimensions, staring back at you, watching. You wonder what they'd think of you, this lone traveller drifting through their machinery, wide-eyed and speechless. You are, after all, what they once were. Something curious, something fragile, something falling into a black hole and wondering, is this the end? They must have asked the same thing. And now, they've built megastructures around what was once a cosmic horror. They've tamed the singularity, bent it to their needs. You marvel at the poetry. The thing we feared most, they turned into an engine. You pass under a panel that seems to be emitting low-frequency pulses. Not random, not natural, maybe a signal, maybe a heartbeat. This construct isn't just alive, it's listening. And as you drift past its glowing edges, you feel it invite you to ask the next question. What will you build now that you've passed through? You drift on beyond the megastructure, past the engineered bloom of the black hole's mechanical flower, into a quieter space. But your thoughts are anything but quiet. Because after all that math and metaphysics, one very human, very earth-shaped question starts bouncing around your brain. Have I seen this before? Not in real life, obviously, but on screens, in books, in whispered dorm room conversations and late-night sci-fi binges. Black holes, these colossal, unseeable beasts, have always haunted our imagination. So tonight, as you ride the edge of physics and fiction, let's do what humans do best. Let's talk about pop culture. Black holes have been everywhere, long before we actually saw one. They're in the background of horror films, the plot devices in space operas, the deus ex machina of many a panicked screenwriter. And honestly, they've aged well. Few phenomena have managed to be so terrifying and so fashionable for so long. Take a little cinematic masterpiece you may have heard of, Interstellar. Christopher Nolan's 2014 film gave us Gargantua, the most realistic black hole ever depicted on screen. Why? Because it wasn't just artistic guesswork. The production brought on theoretical physicist Kip Thorne, yes, the Nobel Prize winner, to calculate how light would behave around a real rotating black hole. That glowing halo around Gargantua? That's gravitational lensing done right. The way the light appears to arc over the top and bottom of the black hole is accurate, based on the way space-time bends around such a massive object. It wasn't just CGI magic, it was physics. Ironically, they had to tone it down. The initial render was so realistic that audiences thought it looked weird. So the final version of Gargantua, slightly Hollywoodized, but still remarkably close to the real deal. That film also introduced a lot of people to time dilation. Remember the water planet orbiting near Gargantua's event horizon, where every hour equaled 7 years on Earth? That's not sci-fi silliness, that's relativistic time dilation at work. The closer you are to a black hole, the slower time passes for you, relative to observers further away. It's bizarre, it's unsettling, it's also real. Historians still argue whether Interstellar's ending, yes, the Tesseract bookshelf scene, is scientific brilliance or plot spaghetti. But one thing's for sure, it planted the idea of black holes as transcendent places, not just destructive ones. And it wasn't the first. Way back in 1979, Disney, yes Disney, released a film called The Black Hole, which featured a spaceship getting pulled into a swirling abyss and finding something resembling hell inside. It was trippy, gothic, and ended with what can only be described as a flaming robot crucifixion. Not exactly NASA approved, but hey, they tried. Then there's Event Horizon, a horror film that posits black holes might literally be portals to hell dimensions. Spoiler, you do not want to go through that Event Horizon. It has demons, and blood, and bad interior lighting. Of course, black holes also appear in dozens of Star Trek episodes. where they're used for everything from slingshot maneuvers to time travel to engineering entire plot resets. In Doctor Who, they're fuel for impossible technology. In Rick and Morty, they're joke fodder and metaphysical metaphors. The point is, black holes aren't just scientific objects anymore. They've become narrative devices, the perfect stand-in for mystery, transformation, danger, and possibility. Why? Because they're the closest thing we have to magic that's real. They're invisible. They're all-consuming. They warp time, bend space, and break equations. And they challenge our intuition in ways nothing else does. More importantly, they let us ask questions we want to ask. What happens when we reach the end? Can we escape our own fate? Is there something beyond death, of a star, of a person, of a universe? Can light come back out of the dark? Black holes, in fiction, let us play with those questions safely. They're metaphors for fear, for loss, for rebirth. Falling into one becomes shorthand for transformation. Coming out the other side, that's a story of evolution. And sometimes stories get things right by accident, like the idea that black holes might be gateways, or the thought that information isn't destroyed, just changed, or that time might behave differently when gravity gets weird enough. All of these once seemed like fantasy, but now they're topics in real research papers. Some scientists even acknowledge the inspiration. The boundary between pop culture and academia has always been thinner than we like to admit. And why not? Science fiction doesn't predict the future, it creates the appetite for it. So here you are, inside the most science-fictional part of the known universe, and it turns out the fiction wasn't that far off. Maybe you can survive a black hole, maybe you can travel through one, maybe, just maybe, they're not ends, but edits, places where the story gets rewritten. And as you think about the stories we've told, about falling, bouncing, building, rebooting, you start to appreciate why black holes continue to captivate us. They let us write endings that feel like beginnings. They remind us that even in the face of obliteration there might be options. And maybe that's why we keep putting them in our stories. Because sometimes, a black hole isn't just a plot device, it's a mirror. A reminder that even when things fall apart, something new might emerge from the wreckage. And that maybe, just maybe, we're all in the middle of our own narrative bounce. By now, you've passed through so many cosmic doors, collapsed, looped, bounced, speculated, maybe even simulated, that it's hard to remember where you started. But something hasn't changed. You're still falling, not physically anymore, not through space or time or singularity, but through questions, through possibility, through everything we still don't understand about black holes. And here's the part no one likes to admit, especially after all that impressive theorizing and poetic bouncing. We don't actually know. We don't know what happens at the singularity. We don't know if Hawking radiation really carries information. We don't know if black holes connect to other universes or just destroy everything for good. Despite a century of progress, billions of dollars of research, and more genius-level chalkboards than we can count, black holes remain the deepest mystery in modern physics. And you can feel that now, not in a frustrating way, in a humbling way. There's a limit to what we know, a line in the cosmic sand, and beyond it, the great unmodelled. Still, we're trying. In 2019, we took the first real image of a black hole, the iconic fuzzy orange ring of M87 star, captured by the Event Horizon telescope. That blurry halo wasn't just a victory for astronomy, it was the first time humans saw the shadow of the unseeable. It felt like a curtain had twitched open, and behind it, still more questions. Why do supermassive black holes exist so early in the universe's history? We found them lurking in galaxies just 600 million years after the Big Bang. That shouldn't be possible, not according to our current models. Some scientists now suspect there may be primordial black holes, ones that formed not from stars but from ultra-dense regions of the infant universe. If they exist, they might even make up a portion of dark matter. Yes, that dark matter. The stuff that outweighs visible matter by a factor of 5 to 1, but refuses to interact with anything except gravity. If that's true, then black holes aren't just exotic leftovers from stellar collapse, they're fundamental ingredients of the cosmos. They might be older than galaxies, older than light. And here's another black hole mystery: how do they spin? Most black holes are rotating, some close to the speed of light. That rotation drags space-time around with it in a process called frame dragging. It's not just a theoretical quirk, we've measured it with satellites. But what causes this spin in the first place? And how does it affect what happens inside? Some models suggest spinning black holes could be more stable wormhole candidates than static ones. Others say spin may allow energy extraction, the famous Penrose process we mentioned earlier, but the full implications still being worked out, and don't even get us started on black hole entropy. Yes, black holes have entropy, a measure of disorder or hidden information. The bigger the black hole, the higher its entropy. This goes against the intuitive idea that black holes are simple objects. They're actually incredibly complex, packed with more entropy than any other known structure. This idea led to the holographic principle, which we've already floated through. But the core question remains, where is all that information stored? We've tried to answer it with holograms, soft hair, firewalls, fuzzballs and more, and guess what? We still don't agree. Historians and physicists and cosmologists still argue whether any of these models can fully resolve the information paradox without breaking other things in the process. And maybe, just maybe, that's the point. Maybe the job of black holes isn't to give us tidy answers. Maybe their role is to pressurize our imagination, to act as idea engines, pushing our theories to the breaking point and forcing us to invent new physics just to cope. They already broke classical mechanics. They bent general relativity. They're squeezing quantum theory as we speak, and they refuse to sit still. Even now, black holes are merging in the far reaches of space, producing gravitational waves we can detect on Earth. LIGO first caught one in 2015, the ripple from two black holes smashing together 1 billion light-years away. That ripple travelled across the universe, barely distorted, and nudged our detectors by less than the width of a proton. From that faint nudge we knew. We knew two black holes had become one. We knew space itself could ripple. We knew that black holes aren't just the silence between stars, their voices in a cosmic language we're still learning to translate. And yet, you still feel the fall. You always will, because black holes aren't just objects, they're transitions, from known to unknown, from being to becoming, from structure to mystery and back again. You could explore forever and still feel like you're on the edge of something deeper. Another horizon, another paradox, another question that doesn't just challenge your brain, but your very sense of identity. You've been falling this whole time, not in the help I tripped sense, but in the journey sense, in the there's no going back sense. And here's the truth, we still don't know where the bottom is. Maybe there isn't one. Maybe that's the whole trick. Black holes never let you hit bottom because you're not supposed to. They stretch the fall into an eternity of becoming. Each theory, each measurement, each simulation, just one more step toward a truth that might not exist in a static form. The more we learn, the more we discover how much we don't know. And maybe that's the most beautiful fall of all. Not into destruction, but into curiosity. Endless, exquisite, still deepening. There's a final shift now. Subtle, like a breath you didn't realize you were holding. The fall doesn't stop, because it never truly does, but it changes, softens, slows. You're no longer plunging into the unknown, you're gliding through it. And here comes the last twist. What if you were never outside a black hole to begin with? Yeah, take a second with that one. You've been falling all this time, through ideas, equations, timelines, stars, but what if the thing you thought you entered was in fact your entire universe? It's not a fringe idea. In fact, it's one of the wildest proposals in modern theoretical physics that still manages to get published in real journals and whispered about at real conferences. Our universe may be inside a black hole. Let's walk through it. Black holes, as you now know all too well, are regions of space where gravity is so strong, nothing, not even light, can escape. The event horizon marks the point of no return. But from inside the event horizon, something strange happens. To an outside observer, the black hole is compact, dense, a speck. But to something, or someone inside, space and time are flipped. The singularity becomes your inevitable future. The universe shrinks to a point behind you, and crucially, space expands. Sound familiar? Our own universe is expanding faster and faster, just like the inside of a black hole might appear to its contents. That's the premise, that our universe is the interior of a higher dimensional black hole, born not from a bounce or a simulation, but from the collapse of a massive star in a parent universe. This is more than metaphor. The math actually supports it in certain models, particularly those involving brain-world cosmology and extra-dimensional frameworks. In these models, a black hole forming in a higher dimensional space could spawn a new, lower dimensional universe on the inside. That universe might be ours. Historians still argue whether this counts as science or glorified metaphor, but let's be honest, it's way more satisfying than imagining the Big Bang as a random magic puff. Instead of everything from nothing, we get everything from something else, from somewhere else. A transformation, not a conjuring trick. And if we are inside a black hole, it would explain a lot. The cosmic horizon, the limit beyond which we can't see, might be a version of the event horizon. The expansion of the universe could be the result of the geometry inside a black hole, and the apparent flatness of space-time might come from the shape of a collapsing object seen from the inside out. More provocatively, the black hole that birthed us might still exist in its parent universe, right now. Maybe it's sitting there in a galaxy, indistinguishable from a million others, quietly containing an entire universe within, ours. Which raises the ultimate question, can we ever know for sure? Probably not. If we're inside a black hole, it's closed, one way, no signals escape, no probes return. We're sealed in a self-consistent reality with its own laws, but there might be clues, tiny asymmetries in the cosmic microwave background, oddities in the behavior of dark energy, or even the exact pattern of expansion over time. We don't know yet, but the point is, we're looking. Because that's what humans do. We fall, we question, we explore, and black holes? They're the perfect companions for that journey. They don't just mark boundaries in space, they mark the edges of knowledge, the places where math breaks down and philosophy wakes up. They are mirrors, not of light, but of us. We cast our questions into them and listen for the echo. And sometimes, if we're quiet enough, we hear something back, a whisper, a hum, the slow rhythm of space-time saying, "You haven't reached the end. You're just getting started." So whether we live in a black hole, fall through one, or build engines around them in the future, they'll remain our best teachers. Not because they give answers, but because they refuse to. You realise that now. Black holes are the universe's way of handing you a note that says, try harder. And honestly, that's kind of beautiful, because it means that even here, at the furthest edge of theory and imagination, there's still more to ask, still more to wonder, still more to fall into. So are black holes hiding a secret exit from our universe? Maybe, or maybe they are the exit and we've already stepped through. And maybe, just maybe, you're not falling anymore. You're flying.